It's computer. Perfect.
Okay, now you got to share your screen again.
Thank you. Now I have to share. Thank you. I have 3 assistants here. Fantastic. Okay, so with the help of Lisa, Jose, and Ed from Stanford, I finally arrived to have all ready. So it is a pleasure to have here Erich Reck. This is, by the way, the first meeting of the OCIE seminar this week with the MPP student by an external speaker. So that's a pleasure that Erich is an external speaker to Chapman, but he's not external to the group that organized the seminar. So it's half external, but in any case, we can count him as external on an important respect that after the talk, we will have a dinner. So this is what makes the essential distinction between internal and external. So in this sense, we can count him as an external. Okay, so Erich, I don't know, 1 hour, 55 minutes, 1 hour, and then discussion. Okay.
So I guess I should stay here. Well, thank you very much for the invitation, and it's a pleasure to now talk here instead of just being part of the audience. So I want to talk about Dedekind abstraction. I think in my announcement, it says towards a logical reconstruction and defense. This is a talk, I gave an earlier version of this talk before that Marco has heard, but 4 years ago or so at a conference in Vienna, actually. And at that time, I started talking to Øystein Linnebo, who has done some similar work, which will come up, and we decided to collaborate and develop this further. And then COVID happened and other things. We got busy with other things. So finally, we are coming back to that. I'm picking up that earlier project. So it's joint work with Øystein. Although what I'm presenting today is more from my side. I will point a little bit to what he has done. And it's work in progress. Oops. No.
I think that you have to take it up and down. Up and down. Does not work up and down.
Okay. Yeah, so a quick outline of the talk. So I want to talk about structuralism. First, some general introductory remarks. There are a number of views called structuralism around in the philosophy of mathematics. I'll say a few general things about that. Then I'll zero in on what's called non-eliminative structuralism, of which there also exist a number of versions. And then I will try to talk about, the goal is to talk about a kind of non-eliminative structuralism that is based on what I call structuralist abstraction. So that's different from how it's often presented, these kind of positions. It builds on a remark by Dedekind, but I think it's also, I'm claiming, related to mathematical practice. It's trying to make something explicit that's implicitly part of at least some parts of mathematical practice. Øystein Linnebo and Richard Pettigrew a few years ago already proposed a way of doing this kind of thing. So working out a Dedekindian kind of non-eliminative structuralism. So I'll briefly tell you what they did. It has certain limits, and then the goal is, can we go beyond those limits? So what they do works to some degree, but we are now trying to find a stronger version of that kind of view and a somewhat different version. In particular, it'll be a kind of axiomatic approach. So it will involve an abstraction operator that's meant to satisfy certain axioms or certain conditions. That's the new thing, somewhat new thing. So I'll introduce that. Then I'll sketch why this is a consistent approach. I'll give a kind of relative consistency proof, and talk a bit about what that view is and some immediate consequences of the view of those abstraction principles. That's the core of the talk. Then in part 4, I'll compare it and connect it to what other people have said. I'll connect it with some remarks by Cantor. There's a kind of Cantorian abstraction that's similar. I'll clarify the sense in which this is meant to be used. There's a kind of static and a kind of dynamic understanding of the approach. So I'll tell you what that is about. And the result of the view, the resulting non-eliminative structuralist view, has some similarities to, in particular, Charles Parsons, partly also Stuart Shapiro. I'll make some remarks about an approach by Kit Fine that has been picked up by Leon Horsten recently, and I'll make some gestures towards homotopy type theory also. And then I'll give you at the end, there are some references. So I'll refer to a number of pieces. I've published a number of things on this topic, and I'm also referring to some other standard literature on the topic. So that's the outline. All right. So quickly, what's meant by structuralism in the philosophy of mathematics? Well, the slogan is that according to, if you have a structuralist view, mathematics is the study of structures, at least modern mathematics. Now that's very vague. So what does that mean? Well, here is how a famous mathematician, Poincaré, expressed this early on. So I think this is a view that started to become prominent in the late 19th century, early 20th century. So Poincaré expresses this way: mathematicians do not deal with objects in objects, but in relations among objects. They are free to replace some object by others, so long as the relations remain unchanged. Content to them is irrelevant. They are interested in form only. And I think one can replace form here by structural. So that's an early expression, one early expression of structuralism. Now, is that, yeah, okay, yeah. So yeah, I don't know if he uses the term structural, maybe not, but nevertheless, so this is meant to give you a first sense of structuralism, but even given that, so the focus is on relational or structural features rather than sort of the intrinsic nature of the object, some idea like that. Mathematical objects are just positions in structures. Those are the kind of slogans one hears. But still, mathematical structuralism, one can mean a number of different things by it. In an early piece from 20 years ago or more, I made a distinction between what I call methodological versus metaphysical structuralism. So in terms of methodology, on the methodology side, one can look at the kind of methods mathematicians have developed to study, to focus on relational or structural features. Right? So that's what I would mean by methodological structuralism. Set theory, I think, was partly developed for that reason. The kind of approach the Bourbaki group developed, category theory in a different way, homotopy type theory, and so on. So those are different methods of getting at structural features. Again, I think this started in the late 19th century. I actually want to claim Dedekind was the first one who did it somewhat systematically, but others too, Poincaré and so on, picked up on that. Now, I'm not going to talk about the methodological side very much. I want to focus on the metaphysical side, actually. Metaphysical structuralism, what's meant by that? Well, this concerns ways of thinking about mathematical objects along structuralist lines. Or there are these two eliminative versus non-eliminative versions. According to eliminative versions of structuralism, you, in a sense, want to avoid talking about objects. You want to find a different way of talking about structural features. According to the non-eliminative version, the distinctive thing is to say, you want to say there are these abstract structures and mathematical objects are positions in the structures or something like that. Here's a simple illustration. So if you look at the Dedekind piano axioms, Dedekind piano arithmetic, an eliminative structuralist like Geoffrey Hellman will say in his reconstruction, any statement about the natural numbers is implicitly a statement about all systems satisfying the axioms. So even something like 2 + 3 = 5, according to this, a typical typical eliminative view would translate into, for all systems satisfying the axioms, the 3 element in it, the 2 element in it plus the 3 element in it will give you the 5 element in it. So you have this universal statement, but you are not talking about abstract structures sort of separately. from that. While the non-eliminative structuralists wants to go beyond that and wants to say, no, we want to talk about structures as a kind of entity. So the non-eliminative structuralist wants to say there are the natural numbers. It's a distinctive system of objects, different from other, let's say, set theoretic models of the Dedekind piano axioms. It's a kind of pure model of it. What does that mean? Right, that's the big question. Now, one can avoid doing that. This, I mean, do we really want to go into this metaphysical side? Well, mathematicians have a number of ways of avoiding that, of avoiding talking about these separate pure structures. For example, so these are, again, variants of structuralist views. So some people want to say, Solomon Pfefferman, Isaacson, Tony Martin, Jose Ferreros, they want to say, no, the axioms should be seen as characterizing or defining a concept. And that's all we need to care about. So it's really, we study concepts and what follows from those concepts. We don't need to talk about objects, right? It's really, mathematics is about concepts. But as Charles Parsons has argued, is the notion of concept really clearer than the notion of object? And furthermore, when we do in mathematics study what follows from the axioms or from the concepts in natural number structure, natural number system. So that would be an example of a concept, the concept of natural number system, or model of the Dedekind piano axioms. When we study that, don't we use objects? Doesn't the reasoning involve mathematical objects? So can we really be just sort of pure concept structuralists? That's the response of non-eliminative structuralists. So we really still want to understand this appeal to objects. Now, standard set theory in a way provides us with a way of doing that. It was partly developed for that purpose. So it allows us to construct models of axiom systems and so on, and compare them in model theory and so on. So for example, you can, for the natural numbers, you can then construct a set of finite phenomena ordinals, omega, and treat that as the natural numbers. And you can construct the real numbers in terms of Dedekind cuts. Of course, you can also construct it in terms of Cauchy sequences and so on. That's one way in which mathematics has developed, right? Another way is category theory, and then more recently homotopy type theory, where my brief way of summarizing that would be to say there we restrict the language in a certain sense, so that we don't need to appeal to these objects anymore. We can sort of, the language allows us to focus directly on structuralist features. So in that sense, category theory and homotopy type theory are structuralist approaches, and to some degree eliminative ones. I want to come back to something closer to the set theoretic approach in what I'm doing today. But so I hope that gave you a sense of the sort of, there are a number of options on the table, a number of ways in which we can avoid talking about mathematical objects, in particular these pure structures. But there are some reasons, or some people like Parsons and I think, no, we don't want to go there so quickly. We want to try to understand this talk of pure structures. All right, so that leads to non-eliminative structuralism. So I think the debate in the English-speaking literature started with a well-known paper by Paul Benacerraf, What Numbers Could Not Be, where very roughly Benacerraf said, well, in set theory, we sort of pretend as if the natural numbers are sets of sets. But is that really adequate to mathematics? Which sets are they? And so on. So it's the set theoretic approach, he argued, in a sense, misses the structuralist side of mathematics in a certain way. Now, Benacerraf himself didn't go the step to then be proposing a non-eliminative structuralist view. Another figure here is Michael Resnick. He also was an early philosopher talking about these issues. He too stopped short of proposing a non-eliminative structuralist view. The first one I think, at least the first well-known one, is by Stuart Shapiro. So, and he's probably still the most representative non-eliminative structuralists. So Stuart Shapiro developed this, what's called a structural theory. So in that structural theory, which is somewhat parallel to set theory, it allows you to construct these structures given some basic assumptions. So then you get the natural number structure as this pure structure. And then a number would be, the number 3 would be a position in that structure. So that's the terminology he uses. So that's one approach, develop a structural theory that tells you which structures there are, which of these pure structures there are. Sometimes people think that people identify non-eliminative structuralism with that. I think that's one way of doing it. In fact, Charles Parsons, not long after that, proposed a different version of that, what's sometimes called a meta-linguistic approach. So instead of developing a structural theory, we start from the axioms and somehow reflect on the language in a certain way. It was a kind of meta-linguistic way of thinking about it that's meant to be different from what Shapiro is doing. The results are relatively similar, but it's a different approach. Ed Zalta and his co-worker have offered yet another way of doing that with their object theory. So that's another theory that allows you to introduce and know which abstract structures exist. Hannes Leitgeb has introduced yet another version of that based on unlabeled graphs and so on. So a number of people have proposed special theories that tell you which structures exist. So separate a structural theory or an object theory and so on. So that's maybe the dominant or the most well-known way of trying to develop this view, non-eliminative structuralism. Now, what are they doing? These people, what's sort of the goal here? The way I think about this, and I picked this up from a remark Malcolm made this summer at a conference that I thought was just spot on. No, in Buenos Aires. So I think of these kind of proposals or positions as attempts to clarify how mathematical practice involves reification. So we reify with our D natural numbers or D number 3. What do we mean by that? How could we possibly understand that? It seems to be something we do in mathematics. Can we clarify that? I think these are proposals for how to understand that. More or less far away or close to actual mathematical practice. I think both Shapiro and, for example, Charles Parsons say we are really trying to stay close to mathematical practice. But people complain, for example, in terms of Shapiro's approach, why this funny structural theory? That's not part of usual mathematical practice and so on. So there seems to be something part of mathematical practice that we want to clarify by staying more or less close to the actual practice in a way. Part of what I'm trying to do is I want to, in some sense, this is a claim that I wonder if you find it convincing in the end. I want to stay in a certain sense closer to mathematical practice than they did. But I'll come back to that later. I talked about the natural numbers, the whole natural number sequence, the number 3 and so on, but there are many other examples. I'll stick with the simple example of the natural numbers in what follows, because the main points I want to make, one can make, but there are many other examples. Take the cyclic group with 5 elements, right? Mathematicians talk about that. So you can consider more concrete groups from some other domain, and then here is an instantiation of the cyclic group with 5 elements. Here's another one, but then there's the cyclic group with 5 elements in itself. Right, so that, what's meant by that? Or the real numbers, or the complex numbers, or three-dimensional Euclidean space and so on. Mathematicians seem to appeal to them. I'll actually want to ask you at the end how much you think that is still a common part of mathematical practice. But when I was trained as a mathematician, this seemed part of it very much. So the way I grew up in mathematics, I wasn't immediately led into category theory in a way. I was still trained more set theoretically. This seemed part of it, these kind of remarks. All right, so again, in non-eliminative structuralism, we want to talk about these pure structures versus, or as opposed to, what I will call relational systems, to have a terminology here. So by a relational system, I mean a set with certain relations and functions and so on is defined on them. So something we construct in the universe of sets. The pure structure is meant to be different from them. Right? So the relational structures live in V, this universe of sets. So that's the terminology I want to use. So here is one Shapiro is one example. A pure structure is, quote, the abstract form of a relational system, highlighting the interrelationship among the objects and ignoring any features of them that do not affect how they relate to other objects in the system. So there's this abstract form, and then there are all those more concrete relational systems. So that's that's one way in which the idea has been expressed. And notice this remark, ignoring any features that do not affect how they relate to one another. That's a typical kind of remark here. How is that to be understood? What's meant by that? So a big part of what I'm going to do today is try to explain what's meant by that. I'm getting there. So Dedekind talks about these features that do not affect, that are sort of irrelevant in a certain sense, as foreign properties. This comes up, there's an interesting correspondence between him and his sometimes co-worker, Heinrich Weber. So they wrote a big paper on algebraic number functions and so on together. So they had an extensive correspondence. Now, interestingly, in that correspondence, Weber, so they talk about how should we think about the natural numbers. And interestingly, Weber proposes a kind of set theoretic or class theoretic construction of the natural numbers that's very close to the Frege-Russell definition. So seemingly independently proposes that. So in terms of equivalence classes, so a number would be an equivalence class of classes for Weber. So he says, why shouldn't we think about numbers that way? Here is Frege's response. One will say many things about a class, like one of those equivalence classes, that one would apply to the number only with the greatest reluctance. Does anybody think, or won't we gladly forget, that the number 4 is a system of infinitely many elements? Right? According to this class theoretic approach, that's what you say. The number 2 is a set with infinitely many elements. And he goes on, but that the number 4, now this is an interesting way to put it, is the child of the number 3 and the mother of the number 5, that's something nobody will forget. So those are the properties that matter, the structural relational properties. The others are the foreign properties. Right? Having an element is what he calls a foreign property. All right, but again, how to understand that? Right? That's puzzling. All right. So now the way I want to do that is by using what I call structuralist abstraction. So this is somewhat similar if you know the debate about neologism and the kind of abstraction operators and abstraction principles in neologism. It's a little bit like that, but it's also different. It's abstract. I want to work with abstraction principles, but structuralist ones, and I'll explain what I mean by that. Let's go back to mathematical practice, at least the one I grew up with. So and the one Dedekind started or was a big part of, and the people he influenced. What do we do there? Well, we work with axiom systems, so Dedekind piano axioms or axioms for the real numbers and so on. Then we construct some models, some set theoretic model. That's exactly what Dedekind himself does, or in some way so we construct what, in my terminology, a set theoretic relational system, and then we abstract from that to get to the pure structure. That's what Dedekind is suggesting. So there's a kind of abstraction involved. In a way, the reification I talked about earlier, the suggestion is think about that in terms of a certain kind of abstraction. But what kind of abstraction? What's going on there? So he, yes, it's crucial in this approach. Yeah. So it's unlike, so for example, Shapiro wants his structure theory to be independent of set theory. So that's not part of it here. I want to start with set theory and then add something to it, build on it in a certain way. Here is the relevant remark. Dedekind actually doesn't often talk about it, but there's this one remark where he makes this explicit. So he says, what he has done, this is from Was sind und was sollen die Zahlen in his famous paper. He has defined what it means to be a natural number system. He calls it a simple infinity. Then he has constructed a particular simple infinity. There's an interesting remarks about that, how he does that. For my purposes, imagine he constructed omega, the finite von Neumann ordinals. He doesn't quite do that, but and then he says this: if in the consideration of a simply infinite system n, like the one he just constructed, set in order by a function phi, the successor function, we entirely neglect the special character of the elements, simply retaining their distinguishability and taking into account only the relations to one another in which they are placed by the order setting function phi, then are these elements called natural numbers or ordinal numbers or simply numbers, and the base element 1 is called the base number of the number series n. With reference to this freeing the elements from every other content, abstraction, so the crucial step is a kind of abstraction, we are justified in calling numbers a free creation of the human mind. It's another famous remark by him. I won't go into the creation side, but we can talk about that too later on. For me, it's what I'm trying to understand is, what does he mean by abstraction? How am I supposed to understand that? So my reading that I presented in a number of papers is Dedekind starts with a simple infinity, so a model of the Dedekind piano axioms that he has constructed, and then he uses abstraction to introduce a pure structure in the sense I talked about earlier, and that's the natural numbers. Right? So there are these various set theoretic models, and then there's the natural numbers. So it's a simple infinity who, in a sense, although this needs tweaking, the elements only have structural properties, or they don't have these foreign properties in a way. That's I want to take that seriously. That's what he's doing. Can we do that? Can one take that seriously? Is this coherent? A lot of people have doubted it, or a lot of people just ignore these remarks by Dedekind because I think they don't quite know what to do with them. So how to understand abstraction here, this kind of abstraction? So a typical criticism is that Dedekind is just talking about a psychological process. So we've constructed this simple infinity, and then we just sort of ignore as a psychological process, or mentally wipe away all the other properties, in a sense. So it's just he's just talking about sort of something psychological, not mathematical. It seems mathematically irrelevant. It seems problematic philosophically. Are numbers then what kind of things are they? They're mental things, or and some people have claimed it's inconsistent in some ways. So Michael Dummett, for example, talks about Dedekind's mystical structuralism in that connection. But don't other mathematicians in the 20th century and maybe even today do the same thing when they talk about the cyclic group of 5 elements, and we get there by abstraction. So we have the more concrete groups, and then there's the group itself, that particular one. So is there a way of clarifying what's going on there? It seems to be something mathematicians do, at least sometimes. Has been called into question in connection with Dedekind by various philosophers. Can one defend that and spell it out? That seems to me exactly the kind of task philosophers have, to try to make sense of some part of something mathematicians have said, like Dedekind. So what I'm doing to use a technical term in a way, I'm giving a Carnapian explication, formal explication of that now in what follows. So I'm giving a formal reconstruction what this could mean. So I want to defend it and spell it out a bit more. All right. Now, this has been done before or tried before in this paper by Linnebo and Pettigrew. But before I get there, for a long time, this remark by Dedekind was dismissed as bad psychologistic, as it's usually called, view. We should ignore it. But some people, my dissertation advisor, Bill Tate, in a paper did that. He said, no, we should understand it as a logical thing that's happening, not a psychological process. There's some logical thing happening here. The neo-Kantian philosopher Ernst Cassirer earlier already suggested that. So the suggestion is this is coherent and we should understand it in a more logical way. But how? Linnebo and Pettigrew tried to do that in their 2014 paper. So their basic idea was now inspired by Frege neologism. Let's think about this in terms of an abstraction operator. It's not some psychological process, but some logical mathematical operator. Let's explain how that's supposed to work. In my presentation of it, let me use standard set theory, so Middle-Frankel set theory, as the background theory. So I'm working in it. I think Linnebo and Pettigrew have more in mind working within second order logic or something like that. But for simplicity's sake, let's work in set theory. So what it means then is we have set theory, the set theoretic axioms, then we add this operator, and I'll use this terminology or this symbolism for it. And it's introduced as follows. If you have two relational systems, or set theoretic systems, and elements in them, so element A in one and A prime in another, this abstraction operator will map them onto something, and it will map the two elements onto the same thing if there exists an isomorphism between the two systems that maps the one element onto the other element. Right, so you say you have two models of the Dedekind piano axioms, and then you have an isomorphism between that maps the 3 element in one to the 3 element in the other. These 3 elements, the abstraction operator will map them onto the same object, a new object.
It is work only if there is categoristic, axiom categorical.
It's meant to be applied when the axiom system is categorical, right? Yes, I should have said that. So it's meant that way. So that's that one can try to explore it more generally, but it's meant that way. It's when we have a categorical axiom system, this is supposed to work out as yeah.
So with the cyclic group of 5 elements, is there a categorical axiom system for that?
Yeah.
And it applies to it.
Yeah.
Okay. But, for example, the core group, the triangle group, you have an isomorphism that makes it so
We'll get to that kind of case. So there's a distinction then between rigid and non-rigid systems or cases like that. I'll get to in a moment. I'm assuming that's what you are pointing to. exactly the case you are pointing to is a problem for them eventually. So well, already seeing ahead in a way. Now, the way this is meant is like in neologism that this abstract A, so we have an element in some relational system, it gets mapped onto this new object, new thing. It's meant to be a newly introduced thing, introduced by this process. It's introduced by abstraction. Then once we've defined it that way, so this abstraction operator works on elements as part of relational systems. So it's really a two-place function, actually. It creates an element as part of a system. I can then say, given some relational system, some model of the Dedekind piano axioms, we get all these abstracts, these elements. Now collect them together. That gives you a new domain of objects. And then just transfer the structure from the model you have onto that system, that new system. That's so my terminology for that is this bracket S. That's that new system. So with this process, we can introduce a new system by introducing these elements and then transferring the relations and so on onto that domain, that new domain. Now, the intention here is what we want, and we don't quite get it, but almost, that when we have two isomorphic systems we start with, then the abstract, I'll call the thing we get the abstract. The abstract of one, of S, and the abstract of S prime are meant to be the same, are meant to come out the same. So isomorphic systems are meant to get mapped onto the same thing. The thing we get is meant to be isomorphic to the original system. That's also important. And the new system is meant to be sui generis in a way, it's newly introduced. And it doesn't have the properties that the model have. Like you start with some set theoretic models, the new system is meant to be not consisting of sets. It's this newly introduced elements. Now, I hope you can see that 1 and 3 are pretty clearly, we get that. But what about 2? And that's exactly the kind of example. So 1 is we isomorphic systems do get onto the same, map onto the same result. It's sort of built into how the abstraction operator works. Right? And it does introduce things that are meant to be not sets. So in a sense, or elements, extra elements. But what about 2? Will the abstract you get always be isomorphic? Turns out no. It works for so-called rigid structures. So when you don't have non-trivial automorphisms, but for non-rigid structures, things collapse, right? One example is the complex numbers with I and minus I. This abstraction operator will collapse them onto one, will map both I and minus I onto the same thing. The simplest counterexample, it's close to what you suggested, is take a 2-element non-directed unlabeled graph. So just 2 things. This abstraction operator will map it onto one thing. It will collapse to 2 things. But then what you get isn't isomorphic already cardinality wise. Right? So it works for the rigid cases, but not for the non-rigid cases. So that would be another example, right? Yeah. So there are many of them. Yeah, the natural numbers and the real numbers, they are rigid, right? And these are the 2 Dedekind was dealing with. So in a sense,
the relative number is not rigid. So it's very easy to have a system that is not
right, yeah.
take the additive group of integer.
Yeah.
It's not rigid.
Yeah.
You don't need to go to the complex.
Yeah, even that, yeah. Now, Dedekind's 2 main examples were the natural and the real numbers. So if that's all you care about, this will work. But if you want it also for those other systems, then no, this won't give you what you want, because you really want that the system is the abstract is isomorphic to what we started with. So, and Linnebo and Pettigrew point that out themselves. So can one tweak this approach, still working with an abstraction operator, so that idea, so that we do get the second kind of result here. That's the task that I remember having a conversation with Øystein a long time ago, but after they had published their article. I thought, I think I have an idea how to do that. And so here is the idea. If you think about it, in a sense, the Linnebo-Pettigrew approach is a kind of bottom-up approach, in the sense that what the abstraction operator gives you are the elements that you then put together to construct a system again. So you work from the elements up. Can we do more a top-down approach? And I think Dedekind wanted a more top-down approach. He didn't, the way I read him, what Dedekind wanted is different. Now here is the basic idea, and I've published this already, the core idea in a paper from 2018. So again, we work with an abstraction operator, but now one that can be applied to whole systems, not just to elements, but systems, relational systems, so sets with relations and functions defined on them. And that also, as the result, as the output, has a whole system as the output. Right, so that's the shift. Yeah, let's assume we are dealing with a categorical model. In some ways, it does require that, yeah. So that's that'll be what I call a top-down approach and a kind of structuralist abstraction. That's what I want to call structuralist abstraction. Now, here is what we want, again, for this principle. The first two here are similar to what I brought up, or the first three are similar to what I had earlier. So let me talk about three abstraction principles or axioms for that operator. The first one is, again, that isomorphic systems get mapped onto the same thing.
But now these are not more theorem, these are action.
Yeah, these are now meant to be axioms for this operator,
Okay.
unlike before. The second one is, again, that the result is meant to be isomorphic to what we started with. And the third one is that we get, so remember, I want to work within set theory, that the result we get does not consist of sets. Right, so the abstraction operator gives us OR elements. It maps into a set of OR elements. Yeah. So the DS is the domain of the new system, doesn't contain any sets. Right, so it's separate from this universe of sets. So in that sense, it's meant to be sui generis. So I'm working with.
Is a proper class.
Right.
Is a proper class.
Right. Yeah. Yeah. So I'm working with some Frankel set theory with OR elements here. That's my background. Now let me add a fourth principle that's more optional, but
sorry, you called it these abstraction principles in the sense that they abstract actions for the abstraction theory, but in the logical sense, these are not abstraction principles.
Yeah, they're different from the neologicist approach. If that's what you mean.
Different actions, but they are not abstraction principles. Right? They are not on the form the operator alpha is identical. The value of I don't know, dollar alpha identical to dollar beta, if alpha and beta have an equivalence relation between them. So they have no form of an abstraction principle in the sense. Yeah,
in particular, I have several. It's not just one thing they satisfy. I wanted to satisfy several things. I mean, my first abstraction principle is somewhat like that, but not the others. That's right. Yeah. I mean, so the idea is I want to work within some of the Frankel set theory of OR elements, add to the language this abstraction operator, and say, let's use these as axioms for the abstraction operator. And then I'm going to ask, is that consistent? Can we do that? Can we add an operator like that to it? In that sense, it's an axiomatic approach. All right, so the fourth one is, what if we have two systems that are not isomorphic, say the natural numbers and models of arithmetic and the real numbers? Should it be possible for them to overlap then when we abstract or not? So my fourth principle says if they are non-isomorphic, the abstract will be separate. Right, so non-isomorphic systems will be mapped onto.
There is a natural one, a rational one, a relative one,
right.
a real one, and the complex one.
Yeah, that's will be the result of it. Right. So if we add that principle to it, then we can show, if it's consistent, then we can show the natural number one and the real number one are different from each other. By construction almost. So are those consistent? Can we do that? Yeah.
Why do you think that's a natural principle? That seems like a very strange thing.
Let me come back to that later. Yes, actually, I wanted to ask you that question. So some people think, Charles Parsons says that he thinks it's part of mathematical practice that whether the natural number two and the real number two are the same or not is left open. He thinks that's how mathematicians think. Would you agree with that or not?
Well, the point is that different, but they always has the problem that they want to say that they are the same.
Right. Most of us want to act as if they're the same. Even though we sort of say, oh, yes, we have to.
Okay, okay. Now let me get back to it. So part of the point here is that one has a choice, actually, the way how you set it up.
The general way to solve the problem is that the structural way. There's a strange that the structural approach take the other direction, but usually it's not relevant whether they're the same or not. What is important is almost yeah, partially there's an embedding.
Right.
So there is an embedding of one system on the other, an embedding of the other.
Yeah. So if you
avoid embedding by definition.
No. No. Exactly. Yeah.
Because otherwise there's no articulation between the
right.
Yeah.
Right.
So usually by construction they are different. Mathematicians say let's consider the embedding and abstract from there and think that they are the same. You are saying please don't do that. Just consider a state different and the embedding should be important for some reason that I guess.
Well, so if I add that principle to it, then I make them different. I insist they're different, and then you do get an embedding, of course, because one is it's not hard to see that there is embedding. Now one can also leave out this fourth principle, and then you leave it open. Right, then you can't prove either way. If you leave out that principle, just from the other three, you can't prove it. So you have a choice. Do you want to add that or not, according to this approach? And one could even then try, I haven't thought this through, could one modify the principle so that the natural numbers then come out as a subset of the real numbers, the abstract? Could one build that in? Maybe I don't quite see how best to do that, but so my point here is that this approach allows you to work with that, to explore different options for that. If you build this in, then you keep them separate. Right?
Yeah, and I think there is an advantage to that because why should we get that the one of the natural numbers is the same as the one of the real numbers when there are actually many embeddings of the natural numbers instead of real?
Yeah. Anyway, we'll come back. I can come back to that. Yeah. Now, with maybe you think, yeah, that should be consistent, but with neologicist abstraction principles, there's this long debate that some of those principles turn out to be not consistent. So what about this? Can we somehow, can I give you a guarantee in a way that this is consistent, that this works? Can I give a consistency proof? And the danger here isn't like with neologism that the abstraction principle can blow up the cardinality, it can be inflationary. Here the issue is about identity questions. Am I introducing some inconsistency in terms of what's identical or not, possibly?
Is inflation? Can you say that it's not inflation?
In cardinality wise, it isn't.
It's not
Right.
cardinal.
Yeah, it's not right. What the abstraction operator gives you has the same cardinality as the one before.
There is a strict definition of the different sort of inflammatory, it's fine, limit of
Oh, okay.
there is some sort, it's inflammatory in the sense that not in
Yeah. It does introduce new elements, but yeah.
I don't know.
Right.
There is
Yeah.
a different sense of inflammatory with respect to one of them, of course, if your system is inflammatory, with respect to another.
Right. So now let me sketch a consistency proof and then point out some further things that hold if you work with these principles. Okay, so the guiding idea in a way is similar to what Dedekind says and other people say, Cantor, for example, starting with some, say, model of the Dedekind piano arithmetic axioms. In a sense, we want to introduce a domain of objects, indistinguishable objects, and then impose the structure from the original model onto that. Right? But the elements are not supposed to have any distinguishing characteristics in a way. We want to sort of use intuitively some units to which we impose then that structure. But what does that mean? What does this mean? They are indiscernible. How can we then how would we transfer things onto that? So does that make sense, this kind of idea? That is how people often sort of, you'll see Cantor later on talk like that. So let's do it a bit more formally. And so this will consist of 6 steps in the end. So again, we work within some Miller-Frankel set theory with OR elements. Now, when you have a relational system, say a model of the natural numbers or real numbers, we can always look at the equivalence class and the isomorphism. Right, so I use this term way of putting it. For S, some relational system, we get the equivalence class of all the things isomorphic to it, a proper class. The proper class within V, consisting of sets, not OR elements, but sets. Now use a global choice function, a fixed choice function, to select an element from the class, from the equivalence class. Right, so you have a system, go to the equivalence class, and then select an element from it by using a choice function. Now, since we're working with proper classes here, one can actually avoid that with the choice function by what's often called Scott's trick. So instead of looking at the full proper class, you can restrict it somehow by looking at those of lowest rank. So there's a way of avoiding problems with proper classes in doing that. Now, should that thing, so go to the equivalence class and then pick an element, in a sense, an arbitrary element, should that just be the abstract, the result of the abstraction? That is one way to think along structuralist lines in a way. So if we did that, the first abstraction principle would be satisfied, right? Different isomorphic systems would get mapped onto the same because we go to the same equivalence class and then pick something. And it would also be isomorphic. So the first 2 of my principles would be satisfied that way. But, and furthermore, I think some people think of what we are doing, especially within set theory, that way, right? What are the natural numbers? Well, pick an arbitrary model, which is sort of what I'm describing here. Could be any model, pick an arbitrary one. But my third principle would not be satisfied, right? It wouldn't be new sui generis things. It would be, we would still have sets. And we couldn't prove that the 4th one is true or false either. Because that the result of the abstraction is not set theoretic, doesn't consist of sets.
Okay. The intersection
Right, is empty. Right, yeah. So that this is a way of thinking. I mean, this in set theory, we sometimes do this kind of thing, but it doesn't quite give me what I want, but it's sort of halfway there. I want to add some things to it, namely, so do what I just said, go to the equivalence class, pick an arbitrary element, an arbitrary model. Now, choose a set of OR elements of the same cardinality, introduce a new set of OR elements of the same cardinality. And at that point, I can now say, if we start with non-isomorphic systems, keep those separate too or not, right? So I can here, by saying when we start with non-isomorphic systems, say the natural numbers and the real numbers, pick different set of OR elements, non-overlapping set of OR elements, then I would take care of my fourth principle, but I could also leave that out. And then transfer the structure of the arbitrary model onto that set of, onto that domain. That's the result. That's the new system. All right, so start with some system, go to the equivalence class, pick an arbitrary model, and then construct out of it one out of new elements, new elements. That satisfies all four principles then. If I add step 5, I also get my fourth principle here. And seems inconsistent, right? I have used choice function, I've used OR elements. So you can think of it as a relative consistency proof. It looks like this shows that I can do that relatively consistently. I can introduce yeah. Yeah, something like that. Right, with OR elements, right? Yeah.
And I would claim that this is the user practice.
Thank you. That's so in a way I'm trying to just make explicit something that's part of mathematical practice here, and that Dedekind was pointing to. And it gives me a kind of non-eliminative structuralism. Yeah, so that's the point. So
I don't see how you accomplish 4 with it. I can guarantee that because these things have got the same parts. So you don't have a. How do you pick your OR elements? Is this like a choice function from E to the OR elements? In which case 4 wouldn't necessarily go.
Let me come back to that question a little later. So this depends a bit on how this is meant to be applied, this operator. So
One, I had a question about the new element. What does new mean? Are you just coming up with a new set of elements for the right cardinality?
Yeah, we add some new objects, a set of new objects of the right cardinality to the set of sets, just like what we do with working with OR elements in set theory.
I mean, it's just an assumption.
Right, yeah.
Right. In the end of the story, what we are doing is proving consistency by the second model.
Right, that's right. Yeah. But I mean, it's meant to be a consistency, relative consistency proof. It meant to show we can introduce an operator like that with those 4 principles within set theory with ornaments. This is consistent. This much.
There's a business about the quantifiers. So you say for every structure we can get a
Okay.
model.
Yeah. So this is the. I'll come back to that, to those 2 questions. I think. Yeah. There is a question there. Yes. Let me maybe. Yeah. Why?
So you have to say for every 2 unequal structures, I can see or and now for every finite set.
Yeah,
but
you're going to say there is a model, so
So
that
you-
for every structure.
Yeah.
Then
Let's get back to that. But Yeah, I'm actually very curious about that point myself, but
Let's leave Professor Reck to finish.
yeah. Now, just one remark, why did I go through this whole thing with the whole equivalence class and then pick an arbitrary model? Well, one point here is that the new system, the abstract, it's meant to be related in the same way to all the instantiations in a way, but it's not meant to be tied to one of them in particular. It's meant to be sort of neutral with respect to all the instantiations, and this does it, right? This going through the whole equivalence class and so on does it. That answers also some questions people have had about non-eliminative structuralism, but let me not go into those. Okay, let me point. I'm a little behind. I hope I can keep going. Here are some immediate consequences. So the first one is, note I can apply this abstraction repeatedly. And so I start with a set theoretic system, I introduce the abstract, and then I can apply the abstraction operator onto that again, but it'll give me the same thing again. Right? So applying it twice won't give me something new. This follows directly from the first two abstraction principles, right? Because the original system will be isomorphic to the one I get by abstraction. So if I apply abstraction to those two, clearly I will get the same thing again. So it's possible to repeat doing it. It's just not very interesting.
I'm sure because the new structure is not the same anymore, so there is no class, there is no equivalence class of things as much.
Yeah, I think that's, let me also come back to that. Yeah, yes. So to be able to do that, I would then, once I've introduced an abstract, I would then have to expand things that the process I did before include that. That is right. Yeah. All right.
So then when you do that, if you want to calculate the abstraction, your equivalence classes have changed.
Right.
Your universe is new.
Right.
So you can have a new abstraction that is gets more to the original one, but it's not
But this concept is simply a consistent group. The problem is you realize can start with the group. Bracket S is identical to bracket S is a consequence of the action, but not the fact of the group.
Right, it follows directly from.
No, what I'm saying is that this is not a consequence of the action, because the action to speak about one new things that you are adding and all the other things that already exist. So when you introduce the new elements, you are able then to expand your universe.
Right.
And now, if you want to calculate, and in this new expansion, of course, now the new extractor is going to be one of the elements of the equivalence class. But if you calculate again the abstraction, you need to introduce new elements. And then the structure, the abstraction is not going to be exactly the same, because it's going to be by
I see, yeah.
But by design, it's going to be
Yeah.
No. Okay.
Yeah, let's come back to that.
Let me just say one. So by design, the abstraction of S is different from S. But right, you were claiming I want
Right,
a structure that
right.
is not any of.
Well, it's meant to be not one of the original set theoretic ones.
Yeah.
So there is a question when I applied repeatedly, how it's meant to work. Yeah. Yeah. Okay. Now, I mean, I'm mentioning this partly because when people have talked about kind of structuralist abstraction, various objections have been raised that claim there's a fundamental problem here when I try to do it again or something like that. So. Let me move ahead here. One other remark. In this procedure with the abstraction principle along my lines, I introduced these new pure abstracts, pure structures. Now, if you compare what's true in that pure structure with what's true in an arbitrary model, the same mathematical truths will hold in them. So it's not like this procedure is meant to introduce new truths in terms of internal truths, arithmetic truths. It's not meant to do that, right? In fact, yeah. So in a way, yeah, that's right. That's right. But it's not meant to do that, right? I mentioned that already. If we add my fourth abstraction principle, we do get that these cross-structural identities are always false, but I could leave out that principle. If I add it, then I get a particular version where if I want them to be different, if I want them to be always false, I can do that. I know how to do that. Notice also that if I'm starting with a non-rigid structure, then this will introduce a system that has indiscernible elements in it, elements that have all the same properties. In fact, it has to be that way to get my other principles to work. Right? That's sort of the price to pay to get over the limitation of the Linnebo Pettigrew approach. Right? But that will happen. So I mean, take a two-element non-directed graph. I get this system, the pure structure of the two objects. They are indiscernible. Then, but that's how it's meant to be in a way. Yeah. Okay. Wondering if I should jump over that. So there's a direct connect. I'm trying to build on Dedekind, but there's also a direct connection to what Cantor is saying. But maybe should I jump over that for the sake of time, or you want me to go through that? Okay. All right. I'll briefly do it. So if you look at what Cantor said about in one of his famous papers about ordinal order types and units and so on, what I'm doing here is actually very close to what Cantor is saying. So here is a remark. Cantor writes, every ordered aggregate M, so suppose we start with an ordered system M, has a definite order type, or more shortly, a definite type, which we will denote by M prime. By this, we understand the general concept, he writes. I think he means something like the structure, pure structure, which results from M if we abstract from the nature of the elements M and retain the order of precedence among them. Thus, the order type M prime is itself an ordered aggregate whose elements are units. This sounds exactly like what I'm constructing or what I'm doing here. Now, I notice units, that they are pure units, as he calls them. Now, Cantor also talks about a different kind of abstraction. Here is the corresponding remark. We will call by the name power or cardinal number. So this is original definition of a cardinal number of M, the general concept, again, a kind of structure, which by means of our active faculty of thought sounds very similar to Dedekind. In fact, he's influenced by Dedekind pretty clearly. It arises from the aggregate M when we abstract from the nature of its various elements M and of the order in which they are given. So if we do abstract from both, we denote the result of this double abstraction, the cardinal number of M by M double prime. Since every element M, if we abstract from its nature, becomes a unit, the cardinal number M double prime is a definite aggregate composed of units. So for Cantor, originally, a cardinal number is a set of pure units, indistinguishable units by this process. Now, there's a difference between that. The first kind of abstraction is very close to Dedekind, or my reconstruction. The second is a little different. But if you start with a set, just a set, with a simple kind of structure that doesn't have any relations on them, and do the kind of Dedekind abstraction, you get as the result exactly this what you get by the double abstraction from Cantor, right? So if what you start with is just a set, an ordered set, the result will be a set of pure units, also along my lines. That's sort of the limit case where it's all indiscernible, all the elements are indiscernible. But that's a case, that's a limit case that's meant to be covered. Now my consistency proof in a way was meant to give you a way of thinking about that. What could be meant by pure units here? My consistency proof was meant to indicate a way to think about that. It's in a sense what we are doing is we are introducing these new OR elements that are mathematically indistinct from each other. If we don't have any additional structure, that's all we get. If we want additional structure, we can then transfer it onto it too. So I'm thinking in terms of what Cantor calls pure units in terms of OR elements, newly introduced OR elements. Okay, now this is, I think, related. Sorry that I'm running late. Let me talk about two different ways of thinking about this operator. So in connection with abstraction principles in neologism, most people think of them as you have this abstraction principle and then it sort of gets applied universally. And you wonder whether that's consistent to do that. But you could also think about it in a more piecemeal way, dynamic way, where you don't apply it everywhere, but you apply it just in some case, and then you can maybe apply it again, and so on. Linnebo actually thinks of the neologicist approach that way. He has suggested an approach to neologism along those lines. And I want to think about this kind of abstraction more in this piecemeal way. Think of using the abstraction principle in a kind of dynamic piecemeal way. So we have the universal sets, and then we construct some system in it, given some categorical axiom system. We construct some relational system in it, say omega or the Dedekind cuts, and then apply the abstraction operator to that, right? So particular cases. So the idea is for some canonical systems, axiom systems, and particularly important ones like the natural numbers, the real numbers, the Euclidean space, and so on. That's when we want to do that. That's when we want to introduce these pure abstracts, not generally, just in a targeted way. That seems to be what mathematicians do. Right, so it's meant that way. I hope that answers or addresses it, connects at least with, yeah.
I think you have the communicativity problem. If I build N and then R and then Euclidean space and then C, like when you give me different structures that they do in the forward, how do you guarantee that that's not?
I don't see that they would be different given my principle 4. Oh, I see.
He's working, and then he introduces the abstraction of the natural numbers and the abstraction of the Euclidean space. And then I do the same, but I do my own.
Right.
How do I know that I didn't use pure elements that for my Euclidean space that I'm using for these natural numbers?
Right, yeah. I mean, the way it's meant is that we do this sort of as a mathematical community.
Yeah.
At some point, we introduce the natural numbers, and then we introduce the real numbers, and then we work with that. That's sort of how it's meant.
Yes, because when we speak about the number 1, we understand that we speak about the vector 0, 1.
Right. Yeah, maybe we can come back to that in the discussion later on. I mean, I'm trying to, in a way, one of my main goals is I'm trying to understand what was Dedekind doing. And so I think that's what he had in mind. So if you think of it that way, but of course you can, beyond Dedekind, you can ask these questions more generally too. Now, once I've introduced, another remark, once I've introduced one of those pure structures, I have new elements and I can play with them, right? I can construct new things out of them that is meant to be allowed. So for example, I can introduce the natural numbers by abstraction and then construct a new system by exchanging 1 and 2 and reordering them. The result will be a different system, but an isomorphic one. Right? So, or I can exchange all the even and odd numbers with each other. Given the natural numbers as a pure abstract, those will give you new systems that will be isomorphic. Right? They will be different but isomorphic along these lines. So the natural numbers and the ones where I've exchanged the odd and even numbers are different systems along those lines. But then if I apply abstraction to both, I go back to what I started with. Right? So that's what's happening. I think this, so Russell in particular has these arguments against Dedekind that are based on those kind of considerations. And I think once one thinks things through, it's clear what's happening. There is that the objections Russell has raised, I think, seem to me confused. He seems to think this isn't possible to think through this kind of situation. Anyway, in any case, you can, once you've introduced a system, you can then construct new systems out of it. That's how it's meant.
Like defining the permutation?
Yeah. For example,
system, you can make a permutation of the system, and then you abstract the two systems. One is the original system, and the other the result of the permutation without the same.
Right, that's right.
Why do you want to do that?
You don't really usually want to do that, but it's coherent, right? You can do that. There are some arguments by Russell that suggest structuralists will become incoherent if you think about doing this kind of thing. I don't see that it's incoherent if you think about it along those lines. It may not be very useful. It may not be important to do that. All right, but let me move on. So let me make some remarks about how this compares, this kind of structuralism compares to ones on the market already, as it were. So, for example, Charles Parsons, in his meta-linguistic approach, he wants these cross-structural identities to be indeterminate. So he wants to say whether the natural number 1 and the real number 1 are the same or not should be left open. I can get that along my lines by leaving out my principal 4, right? But I can also add my principal form, and then I get that they are different. Both fit into this framework in a way. So the one where I leave it out, the result will be pretty close to Parsons' view. I think Shapiro sort of changes his view about that. At some point, he thinks they should be, these identities should be determinate, and another point he thinks they shouldn't. Again, my approach is to show we can do it either way. That so I can get something close to what Parsons wants, but along abstractionist lines, not his meta-linguistic lines. And similarly, one can compare then the result of this kind of approach to these other non-eliminativist views. So you'll see in some ways it's very close, but that there are similar kind of observations one can make in terms of comparison, but since I'm running out of time, Let me just mention Kit Fine in a paper has also given a reconstruction of Cantor. So what these remarks by Cantor, Kit Fine has given one based on his theory of arbitrary objects. What I'm giving here is a reconstruction of that also applies to Cantor that doesn't need to use these funny arbitrary objects that Kit Fine has introduced. It just uses Ur elements. So compared to that approach, I'm using Ur elements rather than these arbitrary objects that Kit Fine and Ian Hurston have discussed recently. So in a way, it avoids some odd complications, and again, I think it's closer to mathematical practice than the Kit Fine approach. Yeah, let me not go into that. I think there are some one can talk about some interesting connections to the univalence axiom in homotopy type theory. But my approach is I'm starting with set theory. So I'm partly because I'm interested in interpreting Dedekind, and not only Dedekind, also Cantor and other people at the time. Also in the piano school, as Paolo Mancosu has pointed out, people were talking about abstraction in a way that probably also can be reconstructed that way. So that's sort of where I'm coming from to try to reconstruct that. Yeah, and again, I'm not claiming that this leads to deep new mathematical results, except I've given a new consistency proof here. It's more a matter of trying to make sense. What could Dedekind have meant by abstraction? Can we spell that out a bit more? A particular kind of abstraction and this kind of reification. Can we get at these mathematical objects through abstraction? So this is meant to reconstruct that in a relatively somewhat formal way. That's the goal. Yeah, and I was wondering what you thought, and this came up already earlier. Do you think I am still close to mathematical practice, or has mathematical practice moved away from this kind of thinking?
When we say, for example, to our students, the number 2 is a set, the students look at us what we need, even if they are relevant students. If they never saw set theory, they never knew that the number 2 can be constructed as a set, but then it is not really a set, right? The number 2 is the number 2. So I think this is very close to our practice. But I would say also that I think, if I am allowed some criticism, I think there's something in the notation that hides a problem.
Okay, sorry. Let me just here are the reference.
Okay,
So that was the result.
Okay, thank you. So now we begin with questions. I see whether I'm here because I saw look questions in the Zoom. So if I understand well, the first question, because Ed, I promised the first question to Ed, but Ed is no more there because I had to finish. You were too long, so you have to send to Ed the last part of your talk. Okay, so Jose.
So instead of writing the abstraction, we could write the abstraction sub B, and then this B, then what is inside this bracket is going to be a structure of B.
Yeah.
Right?
Yeah.
So it doesn't make sense, the abstraction of the abstraction, because the abstraction is not part of the.
Yeah, of course.
Right.
So there is nothing like that, you want to say.
Exactly. The abstraction. No. What I want to say is the abstraction of S. This doesn't make sense.
It's an abstraction in a different, different universe. So,
Yeah, that's
So you mean that there is nothing like that?
Yeah, this doesn't exist because if you write correctly, S belongs to the universe D, and then S belongs to B, and the abstraction of B does not.
Is what you mean?
It's not an element. S is an element of D.
Okay, it's an element. Okay, yeah, of
Yeah,
course.
but this is not an element of D. So you
Right.
cannot.
Yeah, I think, and then if you can do that, if you relativize it to the bigger thing, but then it'll be. So if you then get V with, see how I want to write it. This thing then will be outside of the universe we had
Right,
in the
that's
first
the thing.
step.
Exactly.
That, but if it is not an element of V, what is it?
Yeah, it's an extra element, so it's another set that is not part of the original set of our set of all sets.
Yes, but V by definition is not extensible. How can you extend
No,
V?
of course you can extend it because the elements are the same.
Okay, so it's an UR element.
Yes.
That's what you mean. It's not a set, but it's a new UR element.
Yeah, but then S is going to be S.
Yes, but S is in V or without a UR element or with a UR element?
Without your
Okay,
element.
that's what you mean. Okay,
Yeah. Then the abstraction of S is going to be a set of your elements.
so that's what you mean, that S is not an element of V, but S is an element of V plus UR element.
Yes, and then when you want to calculate the abstraction of that, then it's not going to be the same abstraction, it's going to be the abstraction relative to these new numbers. So the double application of abstraction doesn't work, but it's not going to give you.
Now this is forced by the third principle. Right now, what if I weaken the, can we do that? Weaken the third principle that the abstraction just isn't part of V.
Well, I mean, I think it depends on how much work your global choice function is allowed to do. Because if you can do this globally, probably you're already in V, already extending URL.
Yes, but
You
exactly.
always have a proper class of so you can always, so no matter what you're doing, you can find new things to do this with.
But exactly. So the,
But that's
if you
global,
if you
so
use
it's
a
not choice.
sorry, if you use a choice, strictly speaking, the axiom of choice allows you to construct a set starting from given set, not to construct a UR element starting from given set.
Yeah, but you can say global choice says that I can well order all of my universe, including the URL.
So you think that you have a version of global
That's
choice
the way
that take a set and give a new element?
that's what it's intended.
Okay, but so it's not, you are not working in ZFC. You are working in ZFC plus, well, C, in fact, is not C, it's C plus.
Yes.
You are working in zeta F C plus, because this C E is not the usual C, because it does not take a set to give a set, but take a set to give a new element, so it's not a usual C. That's what you mean.
I think so. But that's not so.
No,
I think that's actually consistent with CFC though.
yeah, but it's not strictly speaking ZFC.
There are two choices. One is the function global choice, and the other is the choice that are picked from F or A. Once you have picked the structure S out of the order, so you have S, the equivalence class of S, and then you pick by the global choice one structure there. And once you have done that, then you have to do another choice. Because for every element in there, you mark it to your element.
Yeah, so I got this to be more explicit. That's
But I'm pretty sure that second one is actually consistent with CFC.
Yeah.
I wouldn't know about that.
Yeah, I suppose that it is consistent, but it's not strictly speaking the same theory. Because we have modified the axiom of choice.
As some sort of working mathematician, I would request that when the community says that Z, the integers are also real numbers, then your structures will reflect that. You know, if this is going to be this communitarian version you're talking about, then when I say, well, complex numbers they were first thought of as an extension of real numbers, but the reals are part of that's just simply the axis, right? So I would want my abstraction of C to contain the abstraction of that. As something we've agreed was important to us. just like agreeing that C is an important structure, so it needs, there's common abstraction. I think the relationships between these canonical structures, you would want to be able to reflect into the structures themselves.
Yeah, so the question would be, can I, by changing my principle for, can I get that?
Yeah.
And in fact, Dedekind himself, or it's interesting in Dedekind's case, when he talks about going from the rational numbers to the real numbers, it's not totally clear whether he thinks of it as adding or as introducing a new system.
I know, it's very, I think he's intentionally.
A cut of rational is not irrational. It's code irrational, but it's not irrational.
But he's actually pretty vague about what he means by the equivalent classes.
Yeah. No. But you notice that it is all the paper by Ken Manders that is domain extensions.
Right.
That is exactly the approach, the idea that what you do is not what you say, but what you that doesn't mean that what you say is bad. But what mathematicians do is not that. What mathematicians do is that. So they start with an n and they extend successively. And so the natural one is of course also the real one, because the real number came by extension starting from the natural one. But then, so in this sense, you would suggest that the extension process is not compatible with a structuralist vision.
Well, it's not captured by how I did it so far, but can I modify?
You think that is
to capture that?
Yeah, okay. Okay.
Well, we have to decide, I guess this is like a Parsons idea, that we can think of the complex numbers as completely independent of the real, or we can think of them as independent. We can have both.
Sure, but what Erich is after is not out of the practice, but I think we want to put it into the decision process.
Well, then, why would not have the practice be the decision?
Because mathematicians not living with it. That's the way we talk.
Well, no, but I mean, I think it's possible to both think that you have the concept of the complex number.
Yeah, of course, but that's not the way mathematicians think about it. It's complex.
Yes, when you say that's
Which too, nobody ever asked that. It's interesting, there's a linguistic funny business when it comes to Hilbert space, because everybody's talking about the field of complex and other ways and all that. But a finite, a fixed dimension Hilbert space. For some reason, Hilbert spaces are, it's an indefinite article. And I've never quite understood that, because a three-dimensional Hilbert space is the same as every other one. But that's not, we don't use a definite article. And I find it strange. It's just as kind of work.
Ben.
Thank you for the thought. How do the Euler elements differ from, if you would like to answer this, from Dedekind's article? They seem to have something.
I would, to fully answer that, I have to go back and think about, look again at how he thinks about the arbitrary objects, but his arbitrary objects are not regular mathematical objects, you know, they have this additional property.
Yeah, and I think I read some of that back in the day. And I think the analogy he was thinking about were indefinites in that's what he was going to learn by the polynomial. So the placeholders, the variables, are these indefinites. And I think that's what he was thinking is arbitrary. Arbitrary objects are acting like that. They're like these formal placeholders. So they're playing a different role. I think that was the analogy he was thinking about rather than Euler.
Right, yeah. Well, I want to work with Euler elements.
Yeah.
Which seems a little simpler anyway, but it's also interesting that he does.
Yeah. That's how I remember it. That's the analogy he was thinking.
Going back to this idea of the one of the natural might not be the one of the real and so on. I think that if you want to informally, we usually start this with two structures, and one embedded to one to the other. Right? And then your choice function should do the correct thing respecting this embedding. And then the few elements of one should be exactly the.
So it's a constraint choice. It's a constraint choice.
Yeah, yeah, so once you have.
You cannot choose what you want.
So that I could add that sort of as an additional principle.
Yeah,
yeah,
it's principle that whenever one instructor is embedded to the other, it's irrelevant to the community. So then you have this option of making it after the use it usually, but the embedding is really very important because, for example, if we are thinking just on the additive natural structure of the natural numbers, there are many different embeddings inside the additive structure of the reals. So the one of the natural numbers is the same as the one of the reals, especially arbitrary for this particular example. But it's very relevant when we speak about the more additive end of the structure of the natural numbers in the reals, because there's only one element that could be the image of one, one has to be one. So there's only one possible embedding. In that case, yeah, so we talk a lot about that in mathematics when especially in category. When we say that there is one object that is unique after isomorphism, it's categoricity, but this is too weak. And very often we say there's a unique object that is there's an object that is unique up to unique isomorphism, right? And this is the rigid part. And in category, for example, it's very common. Let's say we have a partition plus category is one category in which you have products and the mineralogy or whatever it is. But then what is a product? Well, a product is determined up to unique isomorphism. But then sometimes when you want to have the whole category and do a construction with that category, you need to specify one particular product. And this is not part of the information that you have when you decide this is a particular structure. So what you're doing is doing precisely that. You're choosing one particular object in the and then you are doing something else with it. You are abstracting.
Okay, I have something to say against you. Okay, no, there is something that I like very much here. That is this idea to try to make it clear what can imagine Dedekind is thinking. But there is something that I do not like, because it means that I think it isn't. But it seems to me that it's too much semantic. So let's try to explain what I mean. So I think that the idea is that in order to have the natural number, you need to have a lot of system of natural numbers, and then to take them till finally the natural number in the end. So you start with an infinity of not an infinity of natural numbers, an infinity of kinds of natural numbers, and finally when you have this infinity of kinds of natural numbers, you have an infinite number. So when you have one kind of natural number, from a structuralist point of view, that's enough. Why I need to multiply things more? I have one system that works as a natural number, that I have a progression, finish. That's all what I need to make mathematics. Why I should multiply progression and then to go to the progression? So in this sense, we can say that the fact that it's inflammatory is a worry. Of course, it's not, by definition, is not cardinality inflammatory, but it is inflammatory in the sense that you have a lot of systems that you do not care in the end of the story, because the only thing that you need is one. That is, but even more than that, I think that you can even be in some sense more economical. That is the following idea. In order to, you need the data seed here. Why you need the data seed? You need the data seed not only because it is a good language for you, you need the data seed for a much more substantial reason, that you have to work on models. Right. So you have to have an axiomatic and a model. Right. If you have not a model, you cannot go right ahead. So, but why do you need a model? Why you cannot make it directly at the syntactic level? So that's what something, that is what, by the way, Frege does when defining real numbers.
but I think that the idea can be generalized. You are a language of second order logic, okay? And you add to this language of second order logic, you add a third level property, okay? Whatever it is. For example, the property of being the property of being a property of being a progression. So it means that this is my second level property, and to say X, it means that the object that fall under X are the progression. Okay? And then you give the axioms, and the axioms are on the sort for any X. The X have the property P is 1, then blah 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 blah. Then for any great X and for any X that belongs to great X, blah 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 blah. And then, for example, you have the type axioms. Okay, and then you have an axiom that says that if you have two property X, P, and another property Y that also have the property P, and there is one object here and object here, you have an abstractor. Okay, X, they're the same that Y if something happens. Okay, and so now you have no model. Now, directly in your axiomatic, which is operation. I make a clear example. This is a little bit confusing. But one thing, and also in a very nice essay on definition of real number by Dana Scott, that is not published but circulating, and I can give you define the real number. So what does it mean to define real number? Like you give the axioms that define the semigroup, an additive semigroup. Okay. So the positive part of it, and then you say that you require that the semigroup is Archimedean, of course, and then when I make it Archimedean, you say that suppose that F and S prime are two semigroup, and you say that for any X, Y is prime and Y prime, such that X and Y belong to F, and X prime and 1 prime belong to F prime. So the ratio of X, Y is the same thing of the ratio of X prime, right? If and only if for any n and n natural number, n is smaller than n y is smaller in this S, smaller S, if and only if n x prime smaller in S prime and y. Okay? And you are given an axiom that says that for any X and Y in F and any X prime in X prime, okay, there is one and only if Y in X prime such that this ratio is equal to 2. Okay, so now you have a unique ratio that is the same object, even if you take the ratio on one system or the other system. It's clear what ratio is the same. So you have how many semigroup you want. But by your definition, you require that the semigroup are all such that for any 3 elements, 2 in the first semigroup and 1 in the second semigroup, there is a 4th element in the second semigroup, such that the ratio of the first 2 elements in the first semigroup is identical to the ratio of the second element. So to impose categoricity, like an axiom. And then you say that what is to be the ratio? A ratio is to be something that is not an object on one system. Because you take a ratio of 2 elements on one system and 2 elements on the other system, and you have that. It's the same object. And when it is the same object, when this happens, so you have an equivalence class that works on 2 elements of the first system and 2 elements of the system. So what is the advantage of this approach? That you have exactly what you have, but without models. So you have no way, no necessity to speak of the procedure because you have no model. Then you can construct a model of it. You can construct a lot of models. But you make the abstraction directly at the synthetical level. syntactical level.
I mean, I'm not sure I know what you mean by not having the UFC. You just didn't also second order stuff.
If you want, what
But second order means you.
I think you do not have a model. You do have no say. I have my axiomatic, I go to the model and I work to the model.
That I see.
Like, whether you are the data C or not, that's not my point. You do not use the data C as the setting in which you construct a model. Okay?
I see that.
If you want to add data C because you are even L2 plus something more, so like you have a very rich system, but you remain at the syntactic level. You do not work at the semantic level. And then you say, okay, I want a model. You construct a model. But what I do not like in this approach, I do not like. It's not that I do not like in your approach. Possibly I do not like in a structuralist approach. Is that you think structuralist is well, you need to go from the axiomatic to the model to come back to the axiomatic. Why? We cannot stay directly on the axiomatic level.
That's awfully close to what almost every type theory wants to do. Remain at the syntactic level. Right? By having these universes and saying you have to in one universe with inequality in the next universe and things like that.
Okay, I mean, that's, I don't follow the details how to do that, but that's really interesting if there's more Frege way, in a way.
Yes, so you want, I was very quick, but
Do you have the paper? You said this was Scott, James Scott.
yes, I am.
Springer.
Yeah. But the detail of it, you have an axiomatic for Archimedean semigroup, okay? And then you have an axiom, a new axiom, let's say for any x, y, s, and any x prime in x prime, where S and S prime are the same group, exists unit y prime in x prime, such that ratio of x, y is equal to ratio of x prime. Okay, so you are given in this way. This is an axiom of continuous. This is equivalent to the Dedekind of continuous. So you say that for any semi-group here, all the other semi-groups are isomorphic in terms of ratio. Okay, and of course to do that you have to define what does it mean for two ratios to be the same. But this is a question of another axiom that tells you that for any x, y in S, and any x prime, y prime in S prime, ratio of x, y is the same object, identity, that the ratio of x prime to y prime, if and only if, and here you have Euclid axiom of probability for n and n natural number, the multiple n x is smaller than the multiple n y, where smaller, of course, is the order on S, smaller in S, is and only if. And x prime, the same multiple, is smaller in x prime of n 1. Okay, this is of course an equivalent relation of pairs, and so this is an equivalent principle, an abstraction principle. So you can take it as an identity, or you want to take an equivalence class if you want, but the Frege this equivalence. And so now we have an object that is not the ratio on S. It's not the ratio on S prime, because it's the same object, whatever semigroup you have taken. So you are making abstraction for the different semigroups without passing to the model. Okay? And my idea now, I did not work on the detail, I work on the few details, so I know very well how this works, because this is what I'm doing, but I have the impression that this idea will then be done in the system. this question simply to take a computer. So you have essentially your approach, but without going to the model.
No, I think, I mean, I was clearly motivated or influenced by Dedekind's approach, and it looks like he started the more model theoretic way of thinking about it in terms of sets and models, and so I'm sort of working out that approach, and this is an alternative.
More historical. So of course, this is an approach. You are right, that approach does not mean that this is better than the other. It seems that logically speaking, this is better than yours because it's less inflammatory, but possibly from the point of view of mathematical practice, your one is more common. So that's not the point whether it's better or not. The question is that it seems to me that you can make essentially the same thing without using that.
Yeah.
But now, the question is more, forget philosophy and make history. And let's go to the definition of natural number by Dedekind in what is I never remember the name. You are German, so what is in German exactly?
Was sind und was sollen die Zahlen?
Exactly. So my point is, I do not see where is the Dedekind construct the model. In your reconstruction, you need, it seems that Dedekind have the axiom of the chain. So you remember what is a chain, define the chain. You know that what is used to define the chain, in fact, is an equivalent to Kernel axiom. It does not use Kernel axiom, in fact, is equivalent. We define the chain as a structure that have oh my God, not subjective, injective, an injective function, blah, 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 you know what it is. And then you say, okay, now I suppose that there is at least one what is called infinite, no, it was,
Simple
what
infinity.
I don't remember.
Simple infinity.
Simple infinity. Yeah. But it does not at all tell nothing about this simple infinity. He said, I suppose there is one. And then he gave this argument, a strange argument about thinking. Thinking. But this, if you take this argument about the thinker, the construction of a model, so you think that in Dedekind really we need to have a model. We cannot simply say that natural number as the element of any structure that satisfies the chain feature. Why we need to pass from the model? I don't think. What the way in which I read Dedekind is that poor Dedekind say, okay, there's auto mathematician make something really new, and mathematicians say, okay, but you speak of something that does not exist. Okay, now I prove that it exists. I give an existence proof. But according to me, this existence proof is not really necessary for the definition of natural number, because the definition is simply what natural number are. Natural number are not all the model of isomorphic to this model, but simply natural number are the element of the progression. And what is a progression? What is fixed by the axiom of a chain. Point. Why we need a model? In Dedekind, we're not speaking here. So it seems to me that you give too much weight to this strange argument about thinking.
Yeah, I can see that you really want to avoid a model theoretic way of thinking about it. And so in Dedekind, there is this infamous part, this theorem 66, I think.
66,
I think so, yeah, where he proves the existence of a simple infinity, and it goes like this: take yourself, your ego, and then the thought.
Then you think it yourself.
The thought of that. I forget the exact way. He constructs a kind of function on that constructs another thought. So you get
you have a thought. What content is you, and then you have a thought. What content is your you that the content is you, and then you have another talk that the content is the content of your talk, of the content of your talk, of the content of you. And so you have in this way a chain, in fact, because this function is of course injective. As injective is the starting element, it's just not part of the chain because it's the first of all. And so it is a model of this axiomatic state. That's why natural number exists because I have a system that is simply infinite. This is a joke. Mathematical speaking, this is a joke.
No,
That's what I
so,
said.
so there's, I think that this is a bigger topic, how to understand that part of it. And the way I basically approach it is he's saying, okay, we need some object and then a successor function on it. And we need one where you always get a new successor, right? And so had he thought of the empty set and the Somelo or the phenomenon construction, he could have used that. He's doing something like that. He just didn't think of this or something. That's one reading of it, I'm saying. Okay, right.
This is one reading. Instead of talk, you take the empty set.
Now I think one can add to that. I think he could. Now that's very speculative. I think one could say he wants to do something even more epistemologically. He wants an object that you can't deny at all. Your ego.
And you just read some card.
Yeah, something like that.
No,
But also, I remember giving I remember giving a talk at one point where I was talking about somewhat similar thing, defending Dedekind, and Crispin Wright was there, and to my surprise, his response was, "Oh yeah, that's how one can explain how infinitely many things exist with the way. If I want to explain to someone, think of infinite many things, well, take some thought and then the thought of the thought and so on. That's a natural way to explain.
This is also Brown.
Yeah, it's
It's also Cartesian.
This is Brown.
It's
Yes, but my point is not whether this argument is good or not. In a sense, it's obviously not good because it's not formal. In a sense, it's obviously good, it's genial, because it gives a fantastic way to think of what is infinity. So that's not my point. My point is not whether an argument is good or not. I think that the argument, in a sense, is not good, it's very good. It's not my point. The point is really useful for the definition of real number or natural number. So take it, is paragraph 66 outside. The definition fall down? I don't think so.
according to my way of reading it,
According to your
that's-
interpretation, yes.
Yeah, so
That's exactly my point.
I think he
According
is-
to your interpretation, without the paragraph 66, the definition of
he needs a model to work with.
Absolutely,
and so-
absolutely.
so
That is absolutely clear.
That is.
And my question is, are you sure that is the only possible way to read Dedekind? We cannot read Dedekind in such a way that you take this paragraph out and the definition does not fall down.
Well, I think there are others, so there may be a way of doing it without that, but I don't see any indication of that in Dedekind in a way. Maybe Frege developed that, but also if you think about what Dedekind says about the real numbers, so he starts with the rational numbers and then he constructs.
No. When they go to another number, is another stop. Because the definition of Dedekind of real number, in fact, is a coding. You give a coding for the real number. But Dedekind does give a coding for the real number.
I read him more model theoretically again. He constructs a model out of he constructs a model of the action of the real numbers as counts.
Okay, if you want.
And
You
then
can
it's
say that
parallel.
it's a
That's why I
code, you
want to
say
read
that it's
both
a
of them
model.
together.
Okay, I do not disagree on that. You can take it as a model. I take it as a code because I don't like semantics. But at the end of the story, it is the same thing. But the definition of natural number is different. The structure is different.
I want to read them as parallel.
When do you see that is similar?
Okay.
One thing that we have that Dedekind doesn't is VFC set theory.
Right.
And so it's just very sketchy if you're reading them because it doesn't have that whole theoretical framework.
However, I want to say that he was the first who suggested thinking of a universe of sets and functions as the framework for thinking about mathematics for objects. I think he is the first one who's suggesting that. He doesn't have an axiomatically, but he starts working with it.
Well, yeah, it doesn't have a lot. You have to talk about the thought. But I mean, it's so sketchy that he has to have that kind of.
So this is like,
Yes, so I don't really see any advantage in that. So you construct a model, this model is constructed with sets, and then you don't want to say that the number 2 is the set that contains the empty set and whatever. Because you don't like to say that. But what is that? You're saying that a number is a property. Really? The number 2 is a property?
no, the number is not a property.
Yeah, you're saying
No,
that. The
no,
number is
no,
the
no,
property of X
no,
and
no, no.
Y. So
The
that's
number
that's
is not a property because this is an identity. An identity is an abstraction principle that takes property on the object. Is that all the idea of Reck? What is an abstraction principle? An abstraction principle introduces an operator, they take a concept and go to object. Of course, in some, this is very dangerous because in some way it's inconsistent, but not always inconsistent. This case is not inconsistent at all. In the case of a principle, it's not inconsistent at all. But of course, the basic idea is you have a work on concept, but as you have an operator that is a function that takes concept and give object. This is an object. It's not a concept. It's an object.
Okay, then what is a function in logic? So you have to introduce function. Is it a symbol? Is it a predicate? What is a function? So what is the function that takes the
operator raster?
Yeah.
This.
Yeah.
The function is this one. In this case, the function. And in this case, the function takes two objects and give an element. What does it take if you want it?
My question is,
What is the problem with this?
my question is, what object is the function?
It's not relevant to me because I'm not interested in semantics. This is totally stupid question. It is a stupid question. I don't want to know. It is a syntactical operator.
It's not
It is a syntactical operator. It is not a semantic. It is not relevant.
You can have playing this as syntactic when you're throwing second order things all over the place.
So we are not to answer it. So it is the same as asking what is the number two. You're saying it is a stupid question. So let's forget about this topic. Because this is what we're talking about. What is the number two?
No, because what is the number two? The number two is an element of a progression. And what is the progression? The progression is a system that satisfies piano, the axiom of piano 2. What I need models? Why I need models?
No, because no mathematician other than you and people that you talk to is going to understand that the number two is precisely that.
What?
Mathematicians don't think that the number two is that. The mathematicians think that the number two is an object that is not a set, is not a property, is not something that.
And that's what I said. It's what I said. The number two is an element of a system that satisfies.
No, this is not what mathematicians.
What is
say
the number
about it. No, mathematicians don't say. So according to you, then the number two could be this chair, the number two could be I, but this is not true.
No, because
It's not the mathematician that is not
because
it's
that's not
the number two. The
That's not
mathematician is
true.
going to say,
That's
no,
not
the chair is
true.
not the
The
number two.
number two is the pole in a structure, but this is Shapiro. Not me.
And
It is also Dedekind under
we could go
a
to
very
any
usual interpretation of
department
Dedekind.
in the world and ask any mathematician that is not a logician, is this chair the number two? And they are going to say, no. And this is the common practice in
No,
mathematics.
I do not say that number two is chair.
But
I
you
say
said
that you
he
can
could be-
define on this chair and the system of all the chair, if you have enough chairs, it's an infinite chair, you can define a succession relation on the chairs that makes the choose chair play in this system the role of the number two. I am not saying that this chair is the number two.
Well,
I do not say. I say
But you say that it's not-
that I can construct a code for the number two using this chair.
And
Oh.
they are going
So
to
what
say,
is the number two?
maybe you're constructing a code, but you're not constructing the number two.
Yeah.
Because the number two is something else.
Of course, I do not want that. It's exactly my point. I do not want the code. I want to remain on the syntactic level. I do not ask what is the number two. What
Okay,
the only
but
thing that I'm interested to is how can I work with the
the
number
fact
two?
that you don't want to ask what is
The
the
question,
number
what
two,
is the number
doesn't mean
two,
that
is
it
a
is
stupid
not an
question.
important question.
What is the number two?
It's a question that
What
you
is
don't
the
know.
number two?
so you try to tell me who my wife is and you list a bunch of, and you list a bunch of properties. Here, he has this color hair.
You are right. My wife is not the number two. I think your wife is not the number two. I know for you.
No, her one is number one.
Exactly. Exactly.
Well, we should
We should probably,
I'm absolutely agree with Jose on this. Because that is not how mathematicians think about that too.
what? Which one?
Yours.
Possibly.
Anyway, wait.
They will concede that, okay, we could do it. That's the most you'll get out of it. They will never agree that it's two. They'll just say, yes, okay, we can do it your way if you insist. But
So you mean that according to number two, the mathematician number two is a set in ZSP?
No,
no,
So what is that?
it is an object. It's not,
That exists independently of us.
it exists.
There, I
independently.
can grab, take it and put in my.
No. because
Yes.
that is
well,
not
pretty
what
close. A
we
lot of
do.
mathematicians are real fun, are genuinely fun.
You can get to it through.
A lot of mathematicians tell it, but synthesis is is a
No, it's
religion.
the same as-
So that means that is a religion.
empty
The
set-
mathematicians believe in the
The empty
religion of
set is
God.
something.
St. Augustine said, don't trust mathematicians.
No, so I think that the question, what is the number two, is not a question that the mathematics, as a very mathematical.
What about the number 5?
The number one is the successor, the successor, the number two. And what is
maybe I
number
can-
two, the successor of zero. And what is zero, the starting point of the progression.
Is the number 5 Julius Caesar?
Sorry?
Is the number 5 Julius Caesar? Julius
Number five,
Is the number 5 Julius Caesar?
I don't know enough about Julius Caesar to tell you.
There are papers written about it.
Exactly, you know, it is a trade-off. But that is an important point, because normally the argument of Frege is used to say that the definition of number two is not good, because the number definition number two that is given in a certain way, for example, in the Frege arithmetic, is not enough to answer the question whether two is or is not Julius Caesar. Julius Caesar is or not a natural number. So this is the usual argument against the definition. But my point is that true, the definition does not tell us whether Julius Caesar is a number two, but not because I have a bad definition too, because I have no good definition of Julius Caesar. My definition of Julius Caesar is not strong enough to allow me to know whether it is number two or not. I don't know enough about Julius Caesar to answer this question. I know a lot about the number two, all what I need. About Julius Caesar, no, I don't know whether it is number two or not. I'm not interested in knowing that because I make a mathematical and Greek history. I can construct a theory of Julius Caesar in which Julius Caesar is not the number two. Or I can construct a theory of Julius Caesar in which Julius Caesar is number two. I don't care. It's not my problem. My problem is that I can work with two,
But-
independent of whether Julius Caesar is not the number two.
Is the number 2 crosser the Rubicon?
I don't know. Depends of I don't know. I have no theory. I have no theorem. I have no theorem. I have no theorem in theory that says the number two cross the Rubicon. But it's not a theorem. It's not a theorem that it did not cross the Rubicon. No more. There is no theorem that says it crossed the Rubicon. There is no theorem that says it did not cross the Rubicon. So I'm not interested in knowing whether it crosses or does not cross the Rubicon. But I have a theorem that says the number two is the first prime number. This I have a theorem. If that's what I need, why anymore?
Is this controversy here related to this a Leibnizian view of equality?
Yes.
It says that equal means they have the same properties. So if I can simply list enough properties, then I told you everything you need to know. I don't think most mathematicians think that. Because the object two is two, and now it has property. That's why I brought up my wife. It's not a matter of no, I mean it's not a matter of listing the properties of Cherry. It's Cherry is this person. I don't think that's the same thing. I don't think most of us think in this Leibnizian way.
In the theoretical problem, for example, I and -5, they have to be different, but there is no property that is not claim about one that can claim about the other.
We're also proper group.
Yeah, so it's regular elements.
So
Okay,
I
so we
think
can sort of see how
I
that
think
comes
like
up in
this
my
view
approach.
of identity. It's convenient, nice, but I'm not sure that that's really how the rest of this thing. And the axiom of extensionality. So when you talk to people about what makes two sets equal, they never mention Leibniz. They only mention the axiom of extensionality.
Of course, that I know. This is the reason for which they was horrified in the theory, and I am horrified at the theory. The theory is a
Okay.
horrible
This is
theory
clarifying.
because it's based on an absurd axiom, like the axiom of intentionality, that say, look, you can speak with a lot of emphasis of something that you don't know what it is. This is what the
Well,
theory
this is
says.
clarifying. So you,
Now, to me, it's quite strange that you say, I do not want to buy your idea what the number two is, but I can buy the explanation of what the number two is using the theory. The theory is a theory of something that we don't know what it is. We don't know what it is, because action of extensionality explicitly say that we do not need to know what it is.
yeah, well, yeah. I mean,
So you have explained to the question what is the number two and explain the number two is a set? No, because you don't know what is a set.
Yeah, but so from a type theory point of view, the quality is typically, you give criteria for saying things that you do. That's what we say, actually.
In piano
So you
arithmetic,
have terms.
in piano arithmetic, there is a nice criterion to say whether the number 1 plus 4 is or not the number 5. I know.
Yeah.
Yes. Plus 1, 4 is or not the number 6? No.
But that's not because they're in a different position on the progression.
The proof is based on the property of the progression, which is an order. In any case, it is a very different philosophical question. And my idea, my point is not that doing this way is good, doing the other way is bad. I can understand that doing the other way can be very bad and capture some intuition of mathematics. I'm nothing against it. I'm nothing against the work. That's not my point. My point is that it seems to me that you can make the same without using models.
Yeah,
And it's better to make the same without using models. I don't know. That's another story. That I really that we want to joke, and so when we joke, we cry, and we think that I am against you and you are against me. That is a joke. The real philosophical point is that you can do the same without models. Same, not the same. You can do something analogous without models. It's better without model or with model, that I don't know. That's why I prefer without model, because I never understood what it's about. That's all. I am the only one in the world that thinks it's right. So as I said, maybe I can think another way.
Let me just make one remark about it. So that's very interesting. You can do quite a bit of what I'm interested that way, but it does involve abstraction in a different sense.
Exactly,
Right.
exactly.
So I was explaining a certain kind
Exactly.
of.
And this is the reason for which at certain moment I asked you, these are not abstraction principles. And what I meant is that they are not to
Not
solve
that kind, right? That's right.
Exactly.
Yeah.
It is something very abstraction-y in a different sense with having the structures and the get the foreign. You know the story about foreign detail, the foreign properties, before you study that.
Yeah.
You don't have.
Right, but
don't
you
have
avoid,
the-
that's another, I consider as an advantage to
Sorry,
avoid
sorry.
that. So I need to have some account of that in terms of all elements and so on. But I was trying to do that.
So that is even worse, because it's by that I see plus your element. So what's your element? This is even a mystery, not a mystery, what is exactly nobody knows. But what is your element? That is really again terrible.
The first time that I heard about set theory in the sense of the power set, I was really very dizzy because all those infinities. But then I felt much better when I realized that there's a countable model of the universe of all sets. So maybe this with semantics. There's a countable model.
There is a countable model. There is a countable model. And there is a countable model by no, sorry. There is a countable model by Logan and Scholar.
Yeah.
Of course, but the voice is countable model, nobody knows how it's done. Because the only thing that you know that it has to be. You have to be by Logan and Scholar, don't work.
Yeah.
But of course you don't know. Show me the countable model.
I'm happy that it exists.
Okay. But nobody has never seen it.
Actually, there's a book by Paul Taylor that I think comes close to doing an actual. His is more type theory, but accountable model, because he bases everything on type theory. So every function is computable. All of the structures are recursively enumerable.
This is a fine idea and the story. What is not computable is mathematics, is mathematics.
Yeah, no,
The only mathematics that is relevant is the one the other is just what philosophy and religion. Right, this is another stuff. No, in any case, I would like to avoid an impression. I like very much what I did. My point is not that what I did is wrong. My point is seems to me that you can make also in another way.
Yeah, okay.
And this other way, I'm not sure if it is the historical, the only point where there is a perhaps disagreement. I'm not sure that your way to read the Dedekind is the only possibility. I accept the idea that this is a possible way of reading the Dedekind, there is no doubt about it. I'm not sure.
Yeah, I would argue it's a more natural way of reading him, but it may be possible to reconstruct some things in Dedekind go on others. But I mean, thanks very much for that, pointing that out. I need to think about that more. And I'm also very, I mean, the way I look at it, as I said, is can we, as a philosopher, can I reconstruct in a way, clarify what mathematicians are doing here? You are suggesting a different way of doing that. And so I was glad to hear that you think mine is relatively close to standard mathematics. That was my sense too.
Well, the question that you started with taking the abstraction operator on the abstraction. Why would you want to do that? I mean, because it's already abstract. Yeah, it's right. I mean,
we may need.
I mean, it's already as it's already grained of experience.
Sort of like we don't.
Exactly the same thing that you do with the dimensional number, and you abstract it, and then you construct something else, you permute it, and you abstract again. Yeah, that's something that we need to do.
I was getting into that because some arguments, like by Russell against structuralism, involve that. So I was trying to work it out so that I have an answer to that, but maybe that's beyond mathematical practice.
Another thing that you can establish if you want to rescue this idea that the abstraction of the abstraction, this is the abstraction, is that whenever you could allow the structure S. I don't know. So I just had an idea, but I don't know. It is not clear.
Okay, so I think that. Thank you very much. How can I? Share and the Zoom.